This week we're going to continue our study of graphs. We're going to define a couple new terms and see how they can be used, and we're also going to learn some algorithms for solving other types of problems that can be modeled with graphs. So first, let's define this word, directed graph. Definition: a directed graph or for short, we could call it a digraph, is a graph in which some edges have a direction. And we use an arrow to indicate the direction. So have an arrow indicating the direction of an edge. So directed edges, the easiest example that you can use to understand why these might be useful are if you have one-way roads. So if you have one-way roads, and say you're a snowplow trying to go through a city and plow all of the roads. Well, when you're a snowplow, you have to follow the traffic rules, so you can't go backwards up a one-way road. So if you're looking for some path that minimizes the time it would take, you might have to include a direction. Well, you will have to include a direction on the roads if you are a snowplow. So let's look at an example of this. So let's consider a street network with a couple roads, and I'm going to draw that here. So this is just to show you what the graph would look, what a digraph could look like. This street network can be represented by a digraph. So let's first draw the street network. So here we'll have some sort of middle city block. Here we'll have a continuation of the block in that direction, or not a continuation of the city in that direction. A continuation of the city in that direction, and we'll do the same on these other sides. And up here, and over here. But in all these spaces we're going to have roads. So let's describe the roads. So right here, it'd be nice if I had yellow chalk to do yellow lines there, but I don't have yellow chalk, so I'll just use white lines and disobey standard traffic rules. Maybe I'll put this arrow in here. So right here, this road will have cars going in that direction up there, and cars going in this direction down there. And similarly, we're going to have a road down here. Let's not be completely practical. Let's assume this city has a road down there where cars are going in that direction like that, and cars are also going in that direction like that. So down here we have a two-lane road where cars are all going in the same direction. Up here we're going to have a two-lane road where in one of them the cars are going in one direction, and in the other the cars are going in the opposite direction. And now in these perpendiculars, let's say the direction, where should I put it? Let's put it here. Let's say the direction goes like that. We'll say this is a one-way road up here, and on this side we'll have that other type of one-way road. So right here we have roads and we have directions that cars are allowed to travel. Now let's turn this into a graph. So right here we have this intersection that'll be useful, that one, and that one. We'll mark those off. Maybe I should finish the sentence up here. This street network can be modeled using this graph. Maybe I should say this digraph. Well, not maybe, I should say this digraph. So this digraph, we'll mark off these intersections. Now, this road is just going in that direction. So we have an edge connecting them and a direction that the edge can go in. A snow plow cannot plow down this way, going up here, going down, because it might hit cars. Well, I guess it can go down that way if it wanted to potentially lose his job. Let's assume that people driving snow plows do not want to lose their jobs by destroying lots of cars. So right here, this can only go in that direction. And we'll use an arrow like this to signify that. And similarly over here, this goes in only that direction, and we'll use an arrow like this. Now in these other two-lane roads, well, here we have two different directions. So that a snowplow, for example, would have to consider going down this way and going down this way. So we'll do two edges. One going in this direction, one going in that direction. And down here, the snowplow needs to do those two lanes, but they go in the same direction. So we still have these two lanes to consider, but they both go in that direction. So if you're trying to find some kind of circuit, then you'd have to obey these directions. Now, in general, a digraph does not have to contain directions on all of these edges. In one of the homework, was it a worksheet or a homework problem? I think it was a homework problem. There's one where you're asked to find an Euler circuit, and there are some directions. Now, the question of whether a digraph has an Euler circuit is much more complicated than a regular graph. So you will not be asked to find a condition or use a condition that guarantees whether a digraph has an Euler circuit. But in the first homework question, I believe it was the first one, I state that, well, I imply that there is an Euler circuit, and there is in that case. But in general, it's quite complicated to find an Euler circuit on a digraph. Now, right here, with this one, we can immediately conclude that there's no Euler circuit. Why? I'll give you a moment to think about that, meaning it might be worth pausing for a few seconds to see if you can figure out why before I say the answer. So try pausing for a few seconds. This does not have an Euler circuit. This does not have an Euler circuit because these have valence 3. Now with regular graphs, having all even valences guaranteed an Euler circuit. But with digraphs, having all even valences does not guarantee an Euler circuit. However, having an odd one does guarantee there will not be an Euler circuit. So this has odd, they actually all have odd valence. You can, well, I'm not going to discuss further about that because that's not too important of a topic. But this one does not have an Euler circuit. Now, we discussed Euler circuits. There's another type of very important circuit in math, well, in graph theory, called a Hamiltonian circuit. Hamilton was also a mathematician. He was a mathematician in the 1800s. He did many things in algebra and graph theory. One of the things he did was he discovered, this is an algebraic result, which is we will not cover in this course. He discovered a set of numbers which formed what is known in math as a division ring. Now, a division ring is defined in the third year of undergraduate mathematics for advanced math majors, and in the fourth year for the other math majors. So we will not cover that. But Hamilton is a very important mathematician. He's probably not like in anybody's top 10, top 15 of all time, but he did discover several things that are quite important. One of the things he did involves graph theory, and this next type of circuit is named after him because he studied them. So let's define it. You can tell how not important he is compared to the greats of math because I don't even know his first name. His name is Hamilton. A circuit that visits each vertex once and only once. Visits each vertex exactly once. Is called a Hamiltonian circuit. Now, we had an Euler circuit. Euler circuits hit each edge once and only once. Hamiltonian circuits are still going to be circuits, so they're going to start and end at the same vertex. But these circuits are going to hit each vertex once and only once. So let's look at an example. I should probably just erase this so I have the whole board. Some of these graph examples we'll do require pretty large graphs. So let's look at this example. Well, I'll give away a large result. Whether a given graph has a Hamiltonian circuit is a very difficult problem in general. There are classes of graphs that definitely do have them. There are classes of graphs that definitely do not have them. But whether a given graph has one, a general graph, whether that has one, is not currently solved in math. It is a very difficult problem. If you could solve it, maybe I shouldn't say this. I could be wrong about this. There are, about 100 years ago, some mathematician or group of mathematicians maybe, had a list of 10 problems. They were called something like problems of the millennium. And if you solved those problems, they would give you $1 million. If you solved one of those problems, they would give you $1 million. And I'm pretty sure this is one of them. Does a given graph have a Hamiltonian cycle? And it is not currently solved. So, if you want $1 million, come up with a proof that satisfies lots of mathematicians. Well, that's one way. There are other ways you can get $1 million. Consider this graph. Consider the graph. I assume there are many ways of getting $1 million. I don't currently have $1 million, so I don't know for sure. But I will assume there are many ways of getting it. Consider this graph. And another one there. So what letters do we want? A, B, C, D, E, F, G, H, I. Consider this graph. So what we want to do here is find some Hamiltonian cycles. So I'll give you one. We're going to start and end at A because why not? It's the first letter. Well, here's one. You can go from A to B, down to I, down to H, over to E, over to F, G, D, C, and A. Notice in that one, we went A, B, I, H, E, F, G, C, or G, D, C, A. We hit each vertex exactly once. We hit every vertex once. So A, B, I, H, E, F, G, D, C, A is a Hamiltonian circuit. So I'll say examples, well, maybe I'll just say is a Hamiltonian circuit. Is a can't spell circuit. C-I-R-C-U-I-T. So there's one example of a Hamiltonian circuit. There is another. Well, there are many. There are several more. What's the other one I want to write down? Let's write down that one. Okay, that one. I'm just going to redraw this graph. Sometimes it's nice to just scribble on a graph like that and see what you're doing. And something we do in a little bit. I find scribbling on the graph the easiest thing to do in order to not make a mistake. On this one, I'll be a little more informal. I'm not going to write out all the nodes. And that's, maybe I will. I'm not going to write out the letters. So we have these nodes. Another one we could have done looks like this. Start here, go from A to C, over to D, up to B, down to I, up to whatever that one is, G, over to F, over to E, down to D, and then back up to A. That path we just chose started and ended at A, and it hit every vertex. So let's write that one down. It was A, C, D, B, I, G, F, E, D, that's not D, G, F, E, H. Oh, I might have called this D when I was talking. That's H, because it's the 8th one. And then back to A is another. Now what if you chose this one? This one I'm not going to unscribble these out. You can find more in this one. I mean, this one's, it has lots of squares on it, so you can find several. What if you started here, went down, well, maybe I'll just say, what if you did this same circuit but backwards? What would that look like? Well, that would be, what, A, H, E, and so on, back to A. We will find in many applications that thinking of one circuit and a circuit going backwards, we will find it useful to think of them as the same. We'll see an application like that in a moment, but I'll just mention that right now. One other thing to mention on a similar vein is, what if you did this circuit? The same path, but you start here. So you start here, you go over, up, down, and then you follow the same path. Don't go into the building in the middle there. Go into the same path, and then wind up there. That we would consider the same circuit as this one. So, going backwards, we'll consider that the same circuit. Starting at a different point in the circuit and then following the same path, we'll consider that the same circuit. Because mathematically, these are the same circuit. And it's just picking a different starting point. So now let's make a remark about, so we have Hamiltonian circuits. We had Euler circuits. Sometimes I find it difficult to remember which name goes with which concept. And even here I do Euler, Hamiltonian, they're off by 100 years, but I mean one of them you hit the edges, one of them you hit the vertices. So I'm going to just condense those two definitions in a remark. 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 Euler circuits hit each edge exactly once. My foam is moving. I have a hunk of foam here holding this board against the wood so it doesn't move. It was slightly misplaced. Okay, where was I? Euler circuits hit each edge exactly once. While Hamiltonian circuits hit each vertex exactly once. So 2 times in a row I started exactly wrong. Wow. I must be conditioning myself to write edge or something. Because both of those, instead of writing X, wrote like a circle for a D or maybe an A. Where was I? Hamiltonian circuits hit each vertex exactly once. So Euler circuits do the edges, Hamiltonians do the vertices. There are a couple ways of remembering this. Euler and edge exactly once. Wow, that's a lot of words that start with E. 4 out of the 7 words up there start with E. So Euler goes with edge. 4 out of the 8 words exactly once is 2 words. Oh no, 4 out of the 7 words. Yeah, okay, 7. Euler goes with edges. Hamilton goes with vertices. Another way of remembering that is Hamilton's a longer name than Euler. Vertex is a longer word than edge. Because I think they're a little easier to confuse. So one, and the book describes this as Euler circuits forbid the reuse of edges. So I'll also include that bit of clarification. That is, Euler circuits forbid the reuse of edges, and Hamiltonian circuits forbid the reuse of vertices. But we will discuss Hamiltonian circuits and Euler circuits. They're a good part of Chapter 1 and 2, and they will be tested. So definitely have these definitions, have them clarified in your head so that when you hear Euler circuit, you think, oh, I need a circuit that hits all the edges. You hear Hamiltonian, you think, I need a circuit that hits all the vertices. Now, as I mentioned before, not all graphs have Hamiltonian cycles. Here I'll go over 2 different families of graphs that do not have Hamiltonian circuits. So, example, graphs without Hamiltonian circuits. I said cycles a few seconds ago. Circuits and cycles are actually the same thing. So right here is one. So we had 4 vertices and 2 vertices, and we're just going to connect everything over here with everything over here. this right here does not have a Hamiltonian circuit. And you can try finding one. Let's say you start and end up here. Well, okay. Try that. And you go over here. Well, you can't hit the same vertex more than once, so now you have to go down here. And then you can go, say, down here. But once you're there, you'd have to go back here, which you can't do. So if you have this type of graph with a number of vertices over here and a different number of vertices over here, and you connect everything on this side to everything on that side, that will not have a Hamiltonian circuit. Another type that definitely will not have a Hamiltonian circuit is one of these square grid type graphs. Now, some of the square grids do. But let's look at this one with 9 vertices. Let's say it's a 3 by 3 in terms of the vertices. And if you want to start and end up here, well, try it. You can go there. Notice if you choose going there, then you'll have to reserve this for the last thing. So we'll go there. You can try there. Well, okay, now we have to go down. Now you have to go over like that. Up. Up maybe, or you could have gone over there. Now, right at this point, you know you can't go over there and back. So you can go up like that. Right there, that doesn't hit everything. Well, that would have hit everything, but it's not a circuit. And you can keep trying other ways of doing this, but it won't work. You can try, say go around all the way and then go over. That won't work. Anything you try, if it's odd by odd, will not work. Now, if it's like odd by even, you can find one. If it's even by even, you can also find one. But not odd by odd. And there are more families of graphs that definitely do not have them. There are families of graphs that definitely do have them. That thing just fell again. I'm going to have to get a bigger piece of styrofoam up there. One other thing we can do with graphs, so we put arrows on graphs to indicate direction. Say you have say you're traveling somewhere, or you're considering a bunch of cities you could travel to, as we will in the next example. Well, what one piece of potentially useful information is the distance between cities. So if you have a bunch of cities and you have distances between them, you can represent that with a graph. And the distances you can represent by putting what are known as weights on the edge. Weights, W-E-I-G-H-T. So you can, in that type of example, you can use like the distance between them as weights. You could use the travel time as weights. If you had something in business, you could use cost or revenue or profit as weights. There are many things you could use as weights. Whatever is the constraint under consideration, you can consider as a weight. So let's example. Consider the graph where the weights. Yeah, I need that styrofoam. That's too annoying to write on right now. Consider the graphs where the weights represent distances between cities. And this is an example from the textbook. The textbook uses Chicago, Cleveland, St. Louis, and Minneapolis. Now, the numbers in this problem work out very well for a couple examples. However, I will find it very annoying having two cities that start with C. So I'm going to change one of them to a city that starts with a letter other than C. I'm going to change Cleveland to Detroit. So these are not going to be exact distances, but they will be different letters. So, but I'm still going to use the same distances they give. The example the book gives is there are people living in Chicago. They want to visit all these cities, see how they can do it. So I'm just changing one to Detroit. Let's see. They put Chicago down here, so I'll call that C. They put Cleveland up here, so I'll call that Detroit. They put Minneapolis down here, so I'll call that M. They put St. Louis there, so I'll call that S. Now, we need distances between all of these cities. Distance from Chicago to Cleveland is 349, so I'll assume distance Chicago to Detroit is also that, even though it might not be. This distance, these distances are in miles, because that's what we use. That's 425 miles, 562, and 774. So this distance, this 841, is that the right number? No, 541. And when I did this example, it was a textbook example. When I worked through it, that number was the largest. Yeah, that's a 5. So that's 541. So for example, the distance between St. Louis and Minneapolis is 562 miles. The distance between Minneapolis, Chicago, 425 miles. The distance from Chicago to Cleveland, they gave as 349, so I'm taking that to be the distance from Chicago to Detroit. Now, all we're doing so far is considering this. I need to give you something to do with this. The goal, starting and ending in Chicago, visit all cities while minimizing, well, visit all cities exactly once while visiting, or maybe I'll say where, starting and ending in Chicago, visit all cities exactly once while minimizing driving distance. And in technical terms, what we're finding here is a minimum cost Hamiltonian circuit. So here our cost is driving distance. Your cost can be anything. So notice how this actually is a Hamiltonian circuit we're trying to find. We're trying to visit each one of these cities exactly once. So if we want to do that, we can do that by finding a Hamiltonian circuit. Now we have the second condition, that we want to minimize driving distance. Doing that, finding that exactly, is not a solved problem in math. But what we will do for small problems, you can actually just list out all of the potential circuits. And that's what we'll do for this one. But for, if you had 6 or 7 cities, there'd be way more than you'd ever want to list. But what we will do for the remainder of this week is discuss a couple of algorithms that we could use to find not necessarily the most minimum, but something close to the minimum. With small numbers of vertices, we will be able to find the minimum. I should not have erased that. I should have erased this. So we have our goal. So what we'll do, in order to find a minimum cost Hamiltonian circuit, maybe I should have erased this so I have the space. We will construct something known as a tree. Now, next week we'll discuss trees in more detail. But here we're going to use the method of trees to find the minimum cost Hamiltonian circuit. That's a lot of words. So what's the method of trees? Well, you might see in a moment how it looks like a tree. Remember what the goal was, starting and ending in Chicago. So let's start in Chicago. Okay, I'll put this in the middle up here. Chicago. What we do here is look at all potential next moves. Well, from Chicago, for now we're not going to pay attention to the weights. We're just going to find all of the potential circuits we could use and then find the smallest weight one. So here, Chicago, we could do one of three things. We could go to Minneapolis, Detroit, or St. Louis. Let's make that line smaller because I have only 3 feet of chalkboard to use after this. So first we could go over, I want to preserve the order I wrote here, to Minneapolis. Or we could go down, well not down, or we could go to St. Louis. Or we could go to Detroit. Well, that's our first move. What about the next move? Notice there were 3 choices in that first move. What about the next move? Well, if we went from Chicago to Minneapolis, there are only 2 other places we could go. Because we can't go back to Chicago without visiting the other 2. Once we do Chicago to Minneapolis, we have only 2 choices. Detroit or St. Louis. St. Louis or Detroit. And similarly in these others, we have 2 choices. Chicago, St. Louis, then you can go either Detroit or Minneapolis. And Chicago, Detroit, after that you can go to either St. Louis or Minneapolis. Well, that's great. We've traveled to 3 cities. What about the 4th one? Well, let's look what we did in this first one. In the first one, we did Chicago, Minneapolis, St. Louis. Well, if we're visiting 4 cities and we visited 3 of them already, well, that tells us where our 4th one is. In that first tree, meaning following this path like that, brings us to Chicago, Minneapolis, St. Louis. Then you have to go to Detroit. Similarly, over here, if you go Chicago, Minneapolis, Detroit, then all you can do next is St. Louis. Now here's Chicago, St. Louis, Minneapolis. Next would be Detroit. Chicago, St. Louis, Detroit. Next would be Minneapolis. Chicago, Detroit, Minneapolis, St. Louis. Chicago, Detroit, St. Louis, Minneapolis. And then finally back to Chicago. So all of these, after hitting the 4th city, are going to go back to Chicago. I'm going to put the fan on so there's some airflow. Now, right here it looks like there are 6 different travel options. There's that one, that one, that one, that one, that one, and this last one over here. But remember what we're doing here. We're trying to find the minimum cost Hamiltonian circuit. So let's not list them all. Let's look at this graph. Let's ignore the numbers on this graph. Well, no, let's not ignore the numbers on this graph. Say you chose this one. Chicago to Minneapolis to St. Louis to Detroit. Back to Chicago. So say you chose, I don't want to have to redraw this graph. Say you chose this, Chicago over to Minneapolis, up to St. Louis, up to Detroit, back to Chicago. Minneapolis is not up to St. Louis. You'd go to south to go from Minneapolis to St. Louis. But in this graph, it's up. The cost of this is going to be this number of miles, plus this number of miles, plus this number of miles, plus that number of miles. Well, if you do that same thing backwards, you're going to wind up with the same number of miles. So this looks like 6 different cycles, or 6 different Hamiltonian circuits. But this is going to take one of them going forward and one of them going backwards. So we can actually eliminate 3 of these. Now, which 3 can we eliminate? Well, to do that, I would recommend listing them. And I guess I am going to erase this. I would recommend listing them and seeing. So I'll do this first one, CMSDC. So let's say there are 6 travel paths, travel routes. Well, maybe I'll use the math word, travel circuits. Why don't I just say Hamiltonian? I defined the word, why not use it? There are 6 Hamiltonian circuits. So the first one is CMSDC, then CMDSC, then CSMDC, then CSDMC, then CDMSC, and CDSMC. So right here we listed all of them. But we will notice, I'm going to erase this graph now. Now that we listed them, we don't need this graph to help us create that list. But let's examine these. Let's look at the first and last one. The first and last one are going to give us the same travel distance. So these are going to give us the same path through the graph, the same cycle through the graph. Because this is CMDSC. No, that's not what it is. This is CMSDC. It goes Minneapolis, St. Louis, and Detroit. This one does the same thing but backwards. It goes Detroit to St. Louis to Minneapolis. So we will consider them the same. Similarly, this one and this one, the second and fourth, we will consider them the same because it's the same forward as and backwards. And similarly down here, we will consider them the same. So this entire analysis that we went through, we found that there are only 3 different travel paths that could be considered if we're trying to minimize the travel distance. So there are 6 Hamiltonian circuits, but let's, I'm lucky that I have a chalkboard, so I can just erase this. If you're taking notes, which you are certainly welcome to do, you might want to rewrite this next thing as a new thing. But I'm just going to say there are 6 Hamiltonian circuits, but there are 3 distinct. Yeah, I'll put distinct on this board. There are 3 distinct Hamiltonian circuits. These 3 right here. And now all we have to do is find the travel time, or the travel distance. So I'm going to do that by drawing I'm going to draw 3 different graphs, and I'm going to mark off the cycle on each one, because it has a reasonably nice visual that I'd like you to see, all 3 of these. So what I'm going to do is, this first one I'm going to put on this board, the second one I'm going to put on this board, the third one I'm going to put on this board. So I'm just going to write CMDSC here. This one will be CSMDC. And this one will be CMSDC. Now I can erase that and draw the triangle. Sometimes that stays up nicely. So what was it? Minneapolis, St. Louis, Chicago, Detroit. Minneapolis, St. Louis, Chicago. So let's look at this path, and then we're going to find the travel distance. C to M. Well, there's C to M. M to S. S to D. And D down to C. Well, there's that one. C, S, D, M. M, S, D, C. That's not C. C. So now we need C, M, D, S, C. And this other one, C to S to M to D to C. So now we just need to add the travel distances. So these numbers here, I'm not going to label all the numbers. I'm just going to label the relevant ones on this graph. That's 425. That's 562. That's 541. I think that's a 1. We have a 1. And that's 349. And you add those four numbers up. I'll just say travel distance. You add those four numbers up, you get 1,877 miles. It's a lot of miles. What about these other two? This one, I wrote these in the opposite order. This one, you get, what, 541 again, 774, 425, 300. You add all those numbers up, you get 2,040 miles. That's a lot of miles. So right here, we know that one's better if you're trying to minimize travel distance. And these numbers over here, 562, 774, 300, and where am I? 349. You add all these numbers up, you get 1,985 miles. So right here, what was our goal? It's always good in math to go back to the beginning of the question and make sure you answered the question. Goal, starting and ending in Chicago, visit all cities while minimizing the miles traveled. So right here, we know this is the smallest of the numbers, so this one will minimize the miles traveled. So we'll say minimizes miles traveled. I'll just put a circle around that. Now, the way we did this problem did not really use much of an algorithm. It kind of used an algorithm in the sense that making that tree is a step-by-step process. But what we really did here was list out all of the choices and then just compare them. With 4 cities, that is not necessarily the worst thing, because you have only these 3 Hamiltonian cycles to consider. There's one of these on the homework. You don't actually have to list out the tree if you don't want to. You could just go to this type of diagram where you actually list out the cycles like this. I kind of like these visuals. But this, finding this is what we would say in math. We found that using brute force. We listed them and then just compared them. Now, with 4 cities, that's quite doable. With 5 cities, it's also doable. Maybe not quite doable. Where I was using the word quite to mean very, not quite to mean whatever the other word, whatever quite's other meaning is. With 5, it is doable, but it's quite annoying. Let's say it like that. Because you'd have to list out a lot more than 3. How many would you have to list out? How many would you have to list out with 5? Let's see. I believe it's 12. Why is it 12? Well, we need a couple definitions and a theorem. Definition. A graph is called complete if it has edges, one edge connecting each pair of vertices. And what's the actual phrase? Yes, if there is exactly one edge connecting each pair of vertices. Now that example we did with 4, that was complete. So right here, is an example of a complete graph on 4 vertices. The way I like to see that it's complete, I think this definition is a little tough to check. The way I like to see it is if it has 4 vertices and it's complete, then each vertex is going to have 3 edges coming out of it. Because a complete vertex or a complete graph means that all of the things are connected exactly once. So if you have 4 vertices, then this one has to be connected to all of the other 3. This one has to be connected to all of the other 3. This one has to be connected to all of the other 3, as does this one. In other words, all vertices have valence 3. Now what about a complete graph on 5 vertices? What would that look like? Where am I? 1, 2, 3, 4, 5. Well, that's not complete. That's not complete. Nor is that. This right here is the complete graph on 5 vertices. And you can check because all of these have valence 4. So this is complete graph on 5 vertices. Now, what if you had 5 cities and you wanted to go through that same process? Well, there's a way of counting the number of potential circuits. Let's look at what we did here. Started here. How many different places could you go? 3. So keep that number in mind. There were 3 places you could go. You have to choose one. Let's say you chose this one. How many places could you go? Well, you can't go back there because you need to travel to the other 2 first. So you can go here, or you can go there. 2. So you had 3 choices, then you had 2 choices. choose one. Well, once you choose that, you have only one choice left. And that's to go there and then back. So the choices we had here were 3 places we could go, and then 2 places we could go, and then 1. The total number of paths, or the total number of cycles you could create from that would then be 3 times 2 times 1, which is 6. And then half of them are going to be the same as the other half. You divide that in 2 and you get 3. What's that with 5 vertices? Well, with 5 vertices, it's similar, but it's different. Well, a little different. Let's say you start and you want to end there. Well, how many choices do you have here? Maybe I'll write choices. Maybe not choices. I use choice for something else. 3 times 2 times 1. Hamiltonian cycles. Because that's what we were finding. So 3 times 2 times 1 is from the previous discussion. Over here, the previous discussion meaning 2 minutes ago or 3 minutes ago. When you're talking math, you kind of lose track of time. So how many Hamiltonian cycles here? Well, we start there. How many places can we go? These are complete graphs we're dealing with, so we can go to all places. That's one of the reasons we will assume complete for these applications, because then we can go from any city to another. And that's relatively standard. So we start there. How many places can we go from there? 1, 2, 3, 4. So that's 4. We have 4 choices. So let's write that down. Let's say we choose one. Let's say we choose this one as our first choice. How many places can we go after that? Well, we can go there, there, or there. That's 3 choices. So let's say we go here. And how about after that? There are only 2 places left. Then you can go up here. Say you choose that one. Well, from there, you'd then have to go over there and back. So that's only 1 choice. So right here, this had 6 Hamiltonian cycles, half of which were the same as the other half, which left 3 that we'd have to consider. This right here, 4 times 3 times 2 times 1, is 24 Hamiltonian cycles. So that means there'd be 12 we'd have to consider, because half of them are just going to be the other half turned around. That's with only 5 cities. If you had 6 cities, you'd have to consider 120 cycles, and then you'd have to think about the 60 of them. If you had 7, you'd need 720 cycles, and you'd have to analyze 360 of them. That's a lot. But how did we get this? This multiplication works. It's a theorem in math called the fundamental counting principle. The fundamental, principle of counting. I think fundamental and principle, those are big words. It's the multiplication counting principle. I like to call it something that has the word multiplication because we use multiplication, and it's a way of counting things. So I'm going to write that down, and then we'll look at a couple other examples of it that aren't just finding these cycles. A couple other examples that might be interesting. So I'm going to write down fundamental principle of counting. That says counting. And that says of. Fundamental principle of counting. If there are x1 ways, so x with a 1 as a subscript, to choose one thing, and, well, common. X2 ways of choosing a second thing after the first thing was chosen. We're doing it second, so it's assuming after the first thing was chosen. So if there are x1 ways to choose one thing, x2 ways to choose a second thing after first thing was chosen, and we extend this, I'll extend that with ellipses, and xn ways to choose the last thing after everything else was chosen. Then the total number of choice patterns is given by their product. Fundamental principle of counting. Sometimes you see it just called the multiplication principle. I think that's what it's called. If you look it up on, I've never looked it up online, but if you do, it's probably called a multiplication principle of some kind. Or maybe it is called this. I've never seen these words used until right now. It's the multiplication principle. Let's just simplify it as that. Where was it? Then the total number of choice patterns is their product. So x1 times x2 times all the way up to xn. Now, I'm never going to ask you to write this down on a test, but you could be asked to use it and interpret it in a couple different ways. So let's look at a couple examples. These examples might not sound like anything we've discussed so far this semester. In a restaurant, there are 4 kinds of soup. So let's just write this down. In a restaurant, there are 4 kinds of soup. Okay, what else do we have at this restaurant? 12 entrees. There are 6 desserts. There are 3 drinks. The question is, how many possible 4-course combinations are there? So how many, I guess a drink is a course, 4-course combinations, 3 drinks. They have more soup choices than drinks. I wonder how that works. How many 4-course, I misspelled course, C-O-U-R-S-E. How many 4-course combinations are there? C-O-N-A-T-I-O-N-S. How many 4-course combinations? Well, this is just an application of the multiplication principle, the fundamental principle of counting. 4 choices of soup, 12 choices of entree, 6 choices of dessert, 3 choices of drinks. On a problem like this, I would let you use a calculator. My reasons for not wanting you to use calculators aren't because I'd want you to write like 72 times 12 on the side and say it's what, 720 plus 144. But for other reasons. But for something like this, I don't care necessarily if you use a calculator. This number is 864 possible combinations. Just multiply them all together. That's the fundamental principle of counting. Why I like calling it the multiplication principle. How about this next example? Let's do one where it isn't just do these numbers all multiplied. A code consists of what? 4 distinct digits. So 0 through 9. 4 distinct digits. And a letter. Let's say it can be capital or lowercase. So I'll say can be, I'll say case doesn't matter. So it can be any letter, capital or lowercase, any English letter. Code consists of 4 distinct digits and a letter, case doesn't matter. How many codes? Well, with something like this, the way I like to figure it out isn't to just go straight to the numbers. I like to actually write out what the code would look like. And then I'd like to write out how many different choices there are in each position. So 4 distinct digits. Well, how many digits are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So that's 10 total digits. So in first position, well, these first 4 positions, we need 4 distinct digits. So in the first position, we can put any of the 10 digits. So there are 10 choices there. What about the second position? How many choices are there? Well, we need distinct digits. We've chosen one here. So we can't reuse this digit. But we can use any of the other 9. So there are 9 choices there. Similarly, for this next one, how many choices are there? Well, we used up 2 digits. So there are 8 left. And here, we need another digit. We used up 3 of them. So there are 7 others we can choose from. Well, that takes care of the digits. What about the letter? Well, how many letters are there? 26. There are 26 lowercase letters. There are 26 capital letters. 26 plus 26 tells us there are 52 choices for that position. So how many codes are there? Multiply all those numbers together. I didn't write down what that multiplication was because I don't have a calculator near me and I didn't want to write all this out. So I'll just say their product, where there refers to these numbers. So you can figure out that number if you want. On something like this, I would again allow calculators. Calculators would be fine on something like this. How about this next one? How about this next one? You wish to arrange five items on a shelf. How many ways can you do this? Maybe I should say in. In how many ways this be done? Well, 5 items on a shelf, there, 5 items, they'll go there. The first position can be taken, you could start over here, I'm going to start over here. The first position can be taken by any of the 5 items. The next position, there are only 4 choices left. The next position, 3 choices left. This position, 2 choices left. And if you choose the first 4, then there's only 1 place for the last one to go. So we have these 5 positions, multiply all these numbers. In this case, you get 120. Some of you might recognize this pattern as something. This right here is one way of defining the factorial. We'll probably talk about the factorial a couple more times this semester. Factorial is it applies to a number. It's denoted with an exclamation point, and what it means mathematically is you start at that number and you just keep multiplying by the numbers until you get down to 1. But right here, you don't have to necessarily know that the answer to this is 5 factorial. You could derive that using the multiplication principle, using the fundamental principle of counting.